We cover the range here from like chickens with multiple toes. Well, they all have multiple toes. Chickens with a mix of different numbers of toes and blueberries and, of course, the alpacas. This was like a ride and a half. Welcome to Absolute Genius, a new podcast series from Thermo Fisher Scientific. I'm Cassie McCreary.
And I'm Jordan Ruggieri, and for today's episode, we keep things in-house here at Thermo Fisher for a wonderful conversation with Marcia Slater.
Marcia is a senior technical specialist for digital PCR and qPCR at Thermo Fisher. She started her career in the lab at the Shearing Plow Research Institute before finding her love of instruments. She's been helping troubleshoot diverse applications with clients for over 20 years now.
We had such a great time learning about Marcia's work experience, her love for PCR, and, of course, her alpaca farm.
No friends like alpaca friends.
Oh, alpaca friends are great, yes, especially her panda alpaca. That's on my list to see for sure.
The Panda Paca fan club.
Well, Marcia, welcome very much to Absolute Genius. I know I am thrilled to have you here. I know Cassie is as well. I think it'd be interesting, on my end, we haven't actually had really any time on, outside of this to talk actually about your personal background and how you got into science, how you got into the industry. I think actually it'd be really cool to dive into that. Can you give us a little snapshot into kind of how your career has developed and how you got into science?
It probably all started with the fact that I grew up on a farm. So I had all kinds of livestock on the farm. And one of the things that was one of my hobbies was I raised a lot of different varieties of chickens. And I would crossbreed them, doing my little genetic experiments as a kid. Got some really wild things. Like I had this one batch of chickens that all of the offspring had 4 toes on one side and 5 on the other side. And I just thought that was really cool. So that started getting me interested in science and genetics. And then kind of one of my other loves is science fiction. And that got me into astronomy because I was interested in space. So I went to Penn State and I graduated in a major that was just called generally science. I really couldn't decide between genetics and astronomy. And then I kind of, not even sure how it happened, but I fell into molecular biology, which combine that, futuristic angle with the genetics. So I graduated with that degree from Penn State and then went on to Rutgers University. And my department was technically plant science, but I was doing molecular biology and DNA work on blueberries.
On blueberries? Were you trying to grow blueberries with 4 toes on one side and 5 toes?
No, but it turns out there's a lot of really cool things you can do with blueberries. And there were some that had some really interesting flavors that, like, if you were to try them, you wouldn't know it was a blueberry. So I was involved with the blueberry breeding projects over in New Jersey. Really, really fun. And then one of the nice things about it was I could tear apart blueberry leaves and plants to get their DNA without feeling any guilt whatsoever.
Oh, good point.
That is a good point. Now, when you were growing up on the farm, were you aware kind of the scientific experiments you were running, or is it more kind of in that context of breeding chickens, or kind of just a cool thing to try and find? Like, did you know? Were you doing all the inheritance plots and trying to see what you could come up with?
If I could go back in time, I would more closely document all the crosses I was making. So I knew in my head what I was doing and trying to do. There are certain genes that are dominant. So, for example, there's a dominant gene in chickens that causes them to lay blue-green eggs. So I would cross those blue-green egg layers with all the other ones that I thought were pretty. So that way I would have a pretty chicken that laid blue-green eggs. But I didn't actually have lab notebooks per se.
So you finished up and you did the blueberries and the molecular biology and everything like that. Where did your career kind of go from there? Like, how did you get to talking to us here in a nutshell?
Well, so when I was in grad school, I really thought that staying in academia would be my future. As a matter of fact, one of my advisors used to call leaving the lab escaping, and leaving academia was escaping. So I was kind of educated to be skeptical of going out into industry. So I decided to take a temporary position at a pharmaceutical company because I just wanted to dip my toe in the water. And I really enjoyed it. The next thing I knew, I was a full-time employee at Burlex. They ended up leaving New Jersey and moving to California. And I was wanting to stay on the East Coast, so I moved to shearing plow. I was doing cardiovascular central nervous system research as a molecular biologist. That was how I got into industry.
So your career, would you say, has not quite gone the route that you would have expected? It's not been the traditional like trajectory since you were expecting to go into academia and then you're like, no, I'm going to try this.
Yeah, I kind of took opportunities as they came along because while I was in shearing, I was doing a ton of PCR. I was kind of like the PCR guru in my department. But then I also ran a multi-user DNA sequencing facility. And so while doing that, I had an ABI sequencer, and I started to really fall in love with all the toys that I was working with. And so I soon found out that I was doing my work more for what technology I could use and being on the cutting edge than for actually asking scientific questions. And so it was a really natural fit for me to join Applied Biosystems. And I joined Applied Biosystems as a sequencing FAS, field application specialist, because I had done so much training and troubleshooting of people in the multi-user sequencing core at shearing plow. But then I very quickly moved over into the PCR area at Applied Biosystems. And that's pretty much where I've been ever since. I just love all things PCR.
A lot of people fall in love with their branch of science or their kind of particular subject that they're interested in. Was there one thing that maybe stood out that in your head, you were like, wow, I actually think these technologies are amazing. I kind of want to learn more about how these technologies are made or developed. Is there any kind of one event or maybe a few events that stood out to you that led you that direction?
Well, I've always really liked understanding technology. So the PCR and even the sequencing gave me a way to not only do an experiment, but just to really understand how things work. And I think the real joy I was taking with those was troubleshooting. I loved it when people would come to me and say, I'm trying to do this, and I like to break apart that experiment and understand it thoroughly. I always found that the experiments and the technology would almost speak to me, at least the data would speak to me. And along the way, I think one thing I could point to was I had a mentor at shearing who his first question would always be, where's your control? And so I think that I took with me whatever I did was, where's that control? So as I was understanding and troubleshooting experiments, I would always look to those controls, and it actually made me really effective at that. And then it just kind of became like, feeding the monster. The more people sent me things to troubleshoot, the more excited and challenged I would get.
I just have to throw this in. Affectionately, in college, I would refer to, not to their face, but outside of it, anybody who was kind of a mentor and didn't realize they were a mentor, they were like my Yoda. That's what I would
It's
call
a perfect description.
Exactly. Yeah. But, even on top of that, there were people that, I would always identify. And I bet you've done the same thing where you're like, I really like what that person is doing in their career. I want to be like that person. So I would really watch them, go to their talks or try to interact with them as much as they want, or as much as I could, so I could learn from them and try to be like them. And so that's been, I think, probably a bigger part of my career, is identifying that person that was like, that's where I want to go next. I want to be doing what that person is doing.
I think sometimes that happens almost serendipitously also, though. Like you just, you come across somebody and you're like, wow, okay, now I do want to, this is somebody I admire. This is somebody I want to keep track of. This is somebody, I like what they're doing, and I kind of want to follow in a similar path. And you just don't even know that it's going to happen. It's just life plants them in your path, and that's awesome.
That's actually how I got to Applied Biosystems. So the field application specialist came out to do my training for my sequencer, and I watched what she did. She spent, I think it was 2 days working with my team in the lab. And the more I watched her, the more I thought, wow, I would love to do what she's doing. She's teaching people. She has this deep understanding of the technology. And so I ended up calling her up and asking about her job and how she got there. And she kind of promised that, hey, if anything comes up, I'll let you know. And sure enough, about a year later, she called me and said, I've gotten a promotion and now my position is open. Do you want to put your hat in the ring? And the rest is history. People are always happy to tell you about their job and what they're doing. So definitely take advantage of that.
Is that kind of like, so if you could go back and tell your younger self when you were starting out in any of the points of your career, is that a piece of advice you'd tell yourself?
The piece of advice that I give is, or I would give, is that your career path will unfold if you just give it time. I've seen people who they think that a certain position is what they want, and maybe they interview for it and don't get it. And I always view that as that's just a step on the path. Don't get down because you're meant to be somewhere else. Just have faith that if you keep doing the right things, your path will unfold the way it's meant to.
Reminds me, I always wanted to be a dentist when I was in growing up. My whole life wanted to be a dentist. And I knew within about 50 hours of observing at dental offices that it was awful. I was never going to be able to do that. But it took a long time to come to terms with it. So it kind of, reminds me of my own path of, just be willing to try new things, talk to people, see what's out there, and it will unfold. And sometimes when things don't work out the way you want them, it doesn't mean it's the end of the world. So it just one step, one sliver of the great things that are to come.
Oh, and I think you've absolutely wound up in the right place, Jordan.
Hosting this podcast.
It's always where I wanted to be. Marcia, going back into PCR a little bit, how long were you working with real-time PCR and qPCR? What did that look like in terms of that career in PCR?
I was the PCR person at Shearing, but that was back in the old days. And just as I was leaving was when the real-time PCR machines were coming out. So the 7700 came out in the late 90s. I started working with that right around the turn of the century. That was when I started doing real-time PCR. And then new machines came out with, more and better features to allow you to have more complex experiments. And then while I was a sequencing specialist, one of the labs that I was supporting was the Vogelstein-Kinsler lab at Johns Hopkins. And I was there one day and they started telling me about this PCR they were doing with just tons and tons of replicates. And I didn't really internalize it right then, but that was actually my first encounter with digital PCR. They were one of the first publications that actually called it digital PCR. But then I started doing digital PCR at Applied Biosystems. I think it was around the year 2010. That was when we had purchased the open array technology. And the open arrays have 3,000 wells per plate. And digital PCR is all about having lots and lots of technical replicates. So suddenly we jumped from, doing 96 and 384 well plates to doing 3,000 wells. That was enough to start giving you some decent statistical power to do digital PCR.
So talking about digital PCR, we will kind of want to dive in a little bit deeper into that and do something unique on this episode, especially since we are joined by such an amazing expert with digital PCR, and talk a little bit about what is it? What is digital PCR? How is it different than real-time PCR? It is there's a lot of buzz around this technology in labs and in the market, and so we think it'd be interesting to kind of dive into that technology.
Well, so what digital PCR does is it takes a reaction and breaks it up into many, many sub-reactions. So in those early days, you were looking at hundreds, hopefully thousands. Now we break a reaction up into tens of thousands of little sub-reactions. But then underneath of that breakout, the question we ask in each of the sub-reactions is simply if it's positive or negative. So each of the sub-reactions has the most simplistic of questions that you're using. But by compiling all of those yes and no answers over, say, 20,000 sub-reactions, 20,000 chambers, we get a very accurate and precise absolute quantity measurement of that target. So that's one of the main reasons why people use digital PCR is to get that absolute quantity. You also tend to have more statistical power when you use digital PCR. So that's a popular reason why it's being used. With how this works, beyond just the positives or negatives, if you get a chamber that's positive, one of the questions becomes, was it only one molecule in there or was it more than one? So with digital PCR, when you separate your material out into these subreactions, each of the targets has the ability to randomly go into any of the subreactions. And that probability that it will land in a well follows a Poisson distribution. So besides this very simplistic plus or minus answer, there's also the Poisson statistics that are the foundation of digital PCR. It's a little more complex than just adding up the number of positives that you see. It's applying this correction factor for the possibility and probability that a chamber had more than one.
We know you hate interruptions, but I promise this one will be worth it. Are you looking to achieve more precise quantification of your gene targets? Have you ever considered digital PCR as a solution? If so, Applied Biosystems QuantStudio Absolute Q dPCR system is for you.
We love digital PCR here at Absolute Genius. If you are looking to quantify AAV viral titers, monitor rare mutations in liquid biopsies, or perform any precise quantification of your gene targets, you'll definitely want to check this out.
The best thing about the Absolute Q dPCR instrument is that it's easy to set up and run. It enables all the necessary steps for digital PCR, compartmentalizing, thermocycling, and data acquisition, to be conducted on a single instrument. The dPCR workflow is identical to the qPCR workflow you are familiar with, to improve ease of use, minimize hands-on steps, and maximize consistency. You can get results in about 90 minutes.
Unlike other digital PCR systems, the Absolute Q dPCR instrument does not use emulsion or other droplet-based methods to compartmentalize reactions. In fact, the microfluidic array plate technology delivers more than 20,000 microchambers with a coefficient of variation of less than 1%.
That's right, Cassie, and you won't waste upwards of 60% of your sample due to dead volume. The Absolute Q utilizes more than 95% of your input sample, so that you won't miss those rare targets or needle in a haystack events. And if you are looking for high-throughput dPCR options, you won't want to miss this. Walkaway automation with the Absolute Q will be available soon. Our automated solutions for high-throughput digital PCR allow you to run over 1,000 samples in as little as 72 hours. The Absolute Q Auto Run dPCR suite delivers a simple and scalable automated digital PCR workflow to enable consistent, high-throughput dPCR.
You can learn more at www.thermofisher.com/absoluteq or visit the Absolute Genius webpage. Again, that's www.thermofisher.com/absoluteq or visit the Absolute Genius webpage.
The Applied Biosystems QuantStudio Absolute Q dPCR system is for research use only, not for use in diagnostic procedures. Okay, no more interruptions. Let's get back to our conversation. Stepping back even one more step. So you talk about, breaking it out into thousands of these sub-reactions, right? Or breaking it into these different chambers. What does that look like? How is that different in digital PCR? What actually happens to that sample?
Yeah, so you're right. In qPCR, you have that one single tube and you get a CT or a CQ value out of it. So it's a single answer that comes out of that tube for real-time PCR. In digital PCR, you take what amounts to essentially the same tube, but instead of getting that CT value, you spread it out before the PCR reaction to all these subreactions. So if you had, say, 100 positives over with real-time PCR, you would have gotten a certain CT value. When you spread that out into these chambers of digital PCR, you might get potentially as many as 100 positives out of, say, 20,000. Now, it might be lower because just by random assortment, some of the chambers may have gotten 2 or 3 instead of only 1. But that's really the difference in how it works. And then we already talked a little bit about Poisson, but one of the interesting things, once you do that spreading out of the sample, we count up the positives and we count up the negatives. It's actually the negatives that are the most important for getting your quantity. Because when we're modeling that data into the Poisson distribution, we only know two things, positive or negative. So if we plot out bar graphs of Poisson of the number that are there, the only group that we know with certainty is the number of negatives. We know that that group is discrete. They're just negatives. That's that bar graph. But then the positives is essentially the sum of all the ones that have 1, 2, or more targets in that. So we don't know any of those single bars with absolute certainty, just the number of negatives. So the number of negatives anchors us in Poisson. And then once we fit that data to the Poisson model, the average number of copies per chamber can be computed. That's called the lambda in digital PCR. And then once you have that, then it gets really easy. So once you know the average, we know the number of chambers that got filled. And with physical wells, we know the volume of those wells. So that lets us get to the copies per microliter. So instead of getting a CT value, which is a timing measurement, we get an absolute quantity of copies per microliter. Or if you want to be really technically correct, it's molecules per microliter of that target.
So in practice, what are common applications then that digital PCR might make sense to have as a tool?
There's a lot of different applications that can utilize digital PCR. Most commonly, I see people who are doing just straight up absolute quantification of their material. That could be for gene expression studies. It could be for a viral titer. We talked about absolute standard curves. One of the uses for digital PCR is to quantify standards to be used for real-time PCR absolute standard curves. With real-time PCR absolute quantification with a standard curve, your quantity is only as good as how well you've quantified those standards. A lot of times, standards that come from a vendor aren't that precisely quantified. So using digital PCR can give you a better quality absolute standard curve if you're doing real-time absolute standard curves. There's other applications as well, and those deal with quantifying a single base change. That's something that's really, really hard to do with real-time PCR. It's possible, but it's often not that straightforward. But with digital PCR, we have the ability to quantify just single base changes. So with that, there are a lot of people who are doing things like looking for driver mutations in a cancer sample. And then the same exact chemistry that allows you to look at, say, a oncology mutation can also be used to look at variants in microbes. So if you were genotyping a microbe, you need a percent of how much of that base is there to represent the different strains. Digital PCR will let you quantify that.
So if somebody's looking at trying to decide qPCR versus dPCR, one of the best things they can do is just look at what is it I'm trying to achieve? And that can kind of start to help them along the way of deciding between the two.
Yep, that is correct. With qPCR, you tend to have a wider dynamic range. So if you have no idea what you've got, you want to just throw it in there, get a quick answer, get an inexpensive answer, qPCR is a great way to go. It's when you want to get more statistical power that then I would move to digital. Digital will have a narrower dynamic range than qPCR, so you need to be aware of that. If you have a really abundant target, you may need to dilute that in order to bring it down into the digital PCR sweet spot. But if you hit that sweet spot, you will get just precision levels that qPCR just can't even dream of.
Data that just you're blown away with, right?
Exactly. I mean, what you're looking for, there's really tight confidence intervals, and that's one of the things that digital PCR can deliver. I always like to say it's data so beautiful, I want to frame it. And I may have on occasion.
I can just imagine Marcia's fridge. It's just full of beautiful digital PCR and probably some real-time PCR data that's just framed and put up there. I can picture it now.
I'm not in my office right now, but if you were to see the walls of my office, yes, you would see a lot of very nerdy things hanging on the walls.
Hey, we're all nerds here. It's awesome.
That's right.
Very cool. Well, Marcia, I want to, talking about your love of technology and kind of how these are built, right? Focusing on digital PCR, what technologies are out there? Are there different approaches for digital PCR and maybe some advantages and disadvantages of those?
So at Applied Biosystems, we believe, and all of our generations of digital PCR have used physical wells. That's actually how digital PCR started. In the early days, it was 96 well plates. And then the second generation of digital PCR were also primarily plate based in the open array and other cartridges that had little reaction chambers. Later came droplets. So droplets are aqueous droplets in an oil background. The concern that I have with the droplets is, are they absolutely uniform? So that's one of the things to be aware of. Also, they're very fragile. So as you handle droplets, you can actually lose droplets if they merge back together. So with physical wells, we know precisely how big that well is. And then one of the really clever things that's done with the chemistry is to use a dye for quality control. So with our Absolute Q system, we use rocks for quality control. So we look at that well, and if that well does not have the target signal, that is a candidate negative well. And so then we look at the rocks. If the rocks is there and it's at the proper amount of rocks, then we know that that is a correctly filled well, that everything is there, and the only thing that's missing is the target. So that's a true negative well. But if the rocks isn't there, then that's an empty well, or if it's not in the right quantity, it's an improperly filled well. Those are removed. Those are false negatives. And I mentioned before that negatives are the most important thing when we're counting up the positive negatives. We have to have that number be perfect.
Interesting. And one more kind of buzzword that I've heard going around at least is dead volume, right? Is there any insight you can give on dead volume? And if somebody is looking to get into digital PCR, why is dead volume such a critical thing to look at?
Yeah. So dead volume, the importance of it's going to vary depending on your application. So if I had boatloads of my target material, if I was maybe manufacturing a nucleic acid and I had liters and liters, dead volume's not going to be a big deal to me, because what dead volume is it's the amount of your material that's just essentially lost in the plumbing of that experiment. It's gone. It's like you've thrown it away. So if you throw a portion of your material away and you have boatloads of it, then I don't care if I lose a few microliters here and there. But if I'm one of those folks that's doing that fine needle aspirate or liquid biopsy or something else that's a really precious experiment, I once worked with a person who was doing an experiment from a space shuttle. You're not getting another chance at that space shuttle experiment. That's a situation where if you lose any amount of that, it's gone, that's it. You can't repeat it. So for those experiments, dead volume is critically important. It's important to have the lowest possible dead volume if you're working with a precious sample like that.
Awesome. Well, talking about cool things and space stations being one of them, are there any really interesting things that you've seen digital PCR be used for?
It's becoming a big thing with cell and gene therapy. And there's a new kind of up-and-coming application that people will refer to as molecule integrity. So it's something that you actually can't even do with qPCR. So you may have noticed that earlier I said that if you want to be totally technically correct, that digital PCR measures molecules. So for most applications, molecules and copies are the same things. But imagine if you had a construct and you not only wanted to know how much of that construct you had, but is the construct intact, versus getting degraded. So with the machines today, you can do a multicolor analysis. They're enabled for high levels of multiplexing. So you can put a different color probe assay spanning that molecule of interest. And then the question you can ask is, are all four colors together in my subreaction, in my chamber? If they're together, then that kind of implies that they were on the same molecule. Think of those as being like tied together with a rope, and they're all being pulled together into the same microchamber. If instead you only have a subset of colors, so if you did a 4-color one and only 2 are there, well, then that molecule is not there in its entirety. It must have been cut apart. Otherwise, all 4 colors would be there. So digital PCR really allows this kind of up-and-coming application to see if what you're doing is intact or if it's been degraded.
What are the practical implications of that? So why would somebody want to see if their molecule is even intact?
Well, so one, they may have actually manufactured a construct that they're moving into a cell line. And so then they're following that. And it's important to know, is the whole thing there as I designed it? Otherwise, I'd be wasting my time on a cell line that doesn't have the proper construct in it. Another area where I see people using this is infectious disease. So one of the questions these folks might ask is that whole, viral genome present, or has it been degraded in the reservoir in the cell? So digital PCR gives us a tool to be able to answer those questions.
All right, Cassie, I see your brain is going to explode. You want to talk about panda alpacas. Is it time to talk about panda alpacas?
I do really need to talk about this. It's not a want, it's a need. So when I alluded to other cool pictures that you might have, I'm talking about the alpacas, Marcia. Could you tell us about the alpacas? Specifically the one that I have in my mind come to call the panda paca.
I'll have to get you a picture of him. So yes, I have an alpaca farm. And so you might ask, why does a scientist have an alpaca farm? Well, at the beginning, I told you that how I got into science was that I grew up on a farm. So I raised virtually every type of livestock that a farmer in the United States might raise. I missed that when I started my career. I missed having livestock. So as I, kind of investigated animals that were out there, and ones that might be easy to keep while having a regular job. I grew up on a dairy farm. Dairy farming and doing anything else that won't work. You have to milk cows twice a day. But alpacas were kind of easy to care for. They were cute as could be. So I fell in love with them, and I bought a few alpacas and started an alpaca farm. And yes, there is a really cute black and white alpaca. His name is Crimson Flame Smoke. And he's a piece of work.
What? You didn't mention it as the coolest name in the history of names.
Well, so alpacas are in the U.S. are usually registered, so they have to have a fancy name. They're also all DNA tested to confirm their parentage. So I even get to do molecular biology with my alpacas.
I love that. So we've talked about a little bit like the let's see, your different toed chickens. We've talked about your crazy blueberries, and we like to ask this question: do you have like any lab oops moments? It doesn't have to be catastrophic. I mean, I will say that.
I probably pushed out of my mind any lab oops moments. I think for me, I'd like to think that any lab oops moments were relatively minor.
I was hoping you were going to say we accidentally bred a chupacabra or something like that.
Well, so I wasn't the one that had the oops. That would be my husband. I was away on a business trip, and he was supposed to be taking care of the alpacas and accidentally left the boys in with the girls. Oops.
We had some magic moments there.
We did. He did. And alpacas have a gestation period of just shy of a year. So he was like worried for a year that I would find out that he had a oops moment, but he confessed before it actually happened. Fun on the alpaca farm.
Fun on the alpaca farm. We've we've touched on this a little bit. Like, you love the technology side of things and all that, but what is about science as a whole that you're like passionate about?
I think for me, the thing I'm passionate about is, this may sound like, a Miss America type of answer, but it's really trying to make the world a better place. Trying to improve the health of people. I have friends and family who've fought cancer. And so I think a lot of what drives me is to try to get us to those answers sooner to help people.
That's awesome. That's such a good answer. Jokes aside, though, you should have been, while answering it, very Miss America-like, waving.
You can send me a tiara.
Don't tempt me with a good time.
That was Marcia Slater, Senior Technical Specialist for Digital PCR and qPCR at Thermo Fisher Scientific. Thank you so much for joining us for today's episode of Absolute Genius. Stay curious, and we'll see you next time.
Oh, the license to get loud.
I'm just going to shout really loud into the microphone.
Just scream the entire intro.
Welcome! Oh, okay. I'll just talk a little bit louder and a little bit closer, and no video for this one, I guess.
The witness protection video.